This video is a video on Chernobyl's 1986 incident strip chart. The HBO series did a great job capturing witness accounts, but as the old Russian adage says, trust but verify. In 1994 interview, Dyatlov stated that there was nothing alarming 7 seconds before the explosion, which could be called the understatement of the century. Part of this review is to attempt to understand how Dyatlov failed to see that every second of this experiment was very alarming. The Vienna report has some choice words. In the chapter on causes of the incident, they listed 6 violations. In hindsight, it's always easier to see the violations. But there are 3 cardinal sins that were foreseeable problems. Number 3, to have all 8 pumps running, and potentially this was an Akimov last-minute idea, as he was overly anxious about this experiment. Number 4, blocking all the steam escape to the turbo generator, likely Dyatlov's idea, written in the procedure. Number 6, disabling the source system, which is part of the ECCS system. Likely Dyatlov's idea, again, listed in the procedure. This last one was likely because Dyatlov had formed the idea that the feedwater system was a cooling system. The report states the basic motive was merely speed, that they had inadequate understanding of the process and a loss of a sense of danger, which the last one, the loss of the sense of danger, was the one that really seemed to summarize it all. They weren't aware. It's basically situational awareness. There was a lack of situational awareness here. Part of the understanding of what happened that night is understanding how the crew mistook the feed water system as a cooling system. Description for the feed water pump specifically says it is to maintain steam drum level in a lost in translation Russian sort of way. There is no other reason for this pump, and cooling is certainly not stated. The idea that the feed water is a cooling system still persists today among nuclear scientists who talk about the incident, and this is probably due to Dyatlov's influence on the early incident reports. Essentially, what Akimov was doing when he was running through the plant, turning valves and pumps, was what the source system was designed to do from the comfort of the control room. As a side note, the term or acronym SAOR, S-A-O-R, was used in the Vienna report, and this acronym would later be changed to ECCS in INSAG 1 and INSAG 7. In the Vienna report, we can see the figure legend includes the term SAOR for items 7, 8, and 11, which are the vectors to push coolant into the core of the reactor in case a runaway reaction were to occur. It helps to know the process to connect it to the trends. Here is the most common RBMK schematic. Like a boiler system, water is the working fluid. Feedwater flow L is pumped to the steam drum to maintain its level while avoiding thermal shock. In the steam drum, water is separated into 2 streams, a liquid stream and a vapor stream. The vapor stream goes to the turbine as flow M. The liquid stream is pumped to the reactor core to produce steam as flow K. As the steam is produced in the core of the reactor, a value indicating the speed of vaporization is the steam void fraction trend P. If no steam is being generated, P equals 0. As more and more steam is generated in the pressure tubes, P increases. The water-steam mixture that exits the reactor core is returned to the steam drum, where it is separated into a liquid and a vapor stream to repeat the cycle. From this diagram, you can see how flows M and L are related. since we are not creating or destroying our working fluid, the mass going into the system is equal to the mass exiting the system at steady state. If flows M and L are unequal, it means we are accumulating working fluid or losing working fluid from the system. If no steam is generated, like P equals 0 or M equals 0, then naturally the feed water flow also goes to 0. Because if no mass is leaving the system, causing the steam drum level to drop, there is no need to add feed water to maintain the steam drum level. Feed water L is only added to the system based on a level control. There is no addition of feed water based on temperatures anywhere in the reactor. Trend S is the steam drum level, which is well controlled by the level control valve. Trend C is the steam drum pressure. If the pressure is too high, pressure relief valves will open to send the excess to the bubbling pools, also known as the ALS system. So this explains the main trends M, L, K, S, C, P of the chart. The remaining trends in order of usefulness are trends A and D are the same power trend on a different scale. Trends E, G, and H are automatic control rods, where 0 means they are not inserted. They provide insight into scala. Trend O is a measure of how wet the steam is. When this value gets drier or closer to 0, it may indicate the steam-water interface is moving deeper into the reactor core. Trend N is the fuel temperature, which essentially is a flat line until the end due to the large range of the scale. Trend B is reactivity, which only appears to be recorded from 0 and higher. It would have been helpful to see how it behaved below 0. Reading strip charts can be somewhat of an art. There's usually a lot more information than can be seen at first blush. When reading strip charts, certain details need to be taken into account. As I explain these four matters with examples, much of the chart analysis is also occurring. Firstly, a trend can look flatlined or not updating. It is stuck on the last value it received rather than capturing current values. Trend L, for example, the feed water flows remains remarkably constant after the initial steam drum level manipulations. And this should be taken into consideration and with caution. Secondly, values or data points are interpolated. Take trend L. Its value is not recorded every second, but rather once every 30 seconds or so. It saved a data point here and another here about 30 seconds apart, and the trending program draws a straight line between these 2 points. This does not necessarily mean that the flow rate was throttled back linearly as opposed to just turned off within that 30-second window. Other trends can be used to refine this 30-second window of time when additional flow was stopped. For example, the steam drum level stops increasing at 1:22:12, and trends related to steam, O and P, resume at 1:22:10. It follows the flow valve or pump was stopped around 1:22:00 or plus or minus 5 seconds. Note, an excess of 150 kgs per second of feed water was added for 160 seconds, which is roughly 6,340 gallons, to raise the level from probably a midway point to an operational level in the steam drums. Thirdly, a value may be out of range, like the power value, for example. Except for when the instability occurs, the power remains at 10% the entire time. Could it have remained at 10% while 6,340 gallons were added to the steam drum? Probably not. The power value is likely fluctuating, but it is reflected as a constant value at 10% because either it is not calculated at low values or the trend is capped at a 10% low value. So even though the value may actually be below 10%, and the trend chart does as well, the recorded values are capped at a 10% or higher. An operator observing this trend may think the reactor is stable at 10% power, when in reality it may be fluctuating wildly under 10%. So note the y-axis for the trend is listed on the left-hand side. And for the power trend, which is trend A, a solid teal line, the bottom line is 0%, and it increases in 10% increments. So the top line is 120%. So you can see that 10% power remaining solid until the instability is probably not an accurate reading either. So this value would be considered maybe out of range, and you can't really see the detail that maybe you might expect otherwise if it was, above 10%, for example. Lastly, it's best to confirm the trend in one variable with another if possible. So like the trends M and L, for example. M is the steam flow presumably going to TG8, and L is liquid flow or feed water into the steam drum. At steady state, so to speak, the initial stage, those two trend lines should be right on top of each other. They are in the same units, kgs per second, and the same range, 0 to 600. So these flow rates are essentially equal at the start. Then, when the water is added to cool, that basically has a cooling effect on the steam drums, those two trends separate. The steam flow seems to drop down to a lower value. It's a light yellow color, it's hard to see. And the feed water rate increases until the feed water additional flow is stopped. So these flow rates are essentially equal at the start. And they then return to being equal just before the start of the experiment. So in addition to trends M and L behaving as expected, the trend S also confirms that the steam drum level is increased, the inventory of the system is increased, there's more working fluid in the system that's been added during that 3-minute period. So it's all matching the expectation by during that time frame. Then there is a flat level in the steam drum for a long while until it has an interesting way of going to 0, as if it is flowing out and not necessarily flashing out. It's parabolic curve. It's a curve that is likely to reflect actual collected data at a more frequent interval. The main idea of showing this entire strip chart on one chart, one page, is that it's only about 8 minutes long. It starts at 1:18 a.m. and ends at 1:26 a.m. So looking at the portions of it, there's 1 minute of steady state, followed by 3 minutes of adding cold water. Then there's another 45 seconds to reach the new steady state. And ideally, steady state would be maintained for at least 3 minutes. 45 seconds seems a little short before adding a new variable or perturbation into the system. So they have 45 seconds of steady state, and then they start the experiment, which ran for about 35 seconds before pushing the AZ5 button. Then another 5 seconds, the main circulation pumps seem to have been starved of water. And then the end of the incident occurs within 3 seconds of that. In my opinion, the events in this 55-second window are the root cause of the incident. In other words, alternate actions taken within that 55-second window may have avoided the incident. To say it another way, The state of the reactor at 1:23:00 a.m. could have been maintained indefinitely without incident. Please let me know in the comments if the reactor would have exploded anyway without performing the experiment at this time. You can see how quickly everything happened. 55-second window for a huge incident like that doesn't seem like a lot of time. And this essentially required sort of race car driver reflexes from the operators. And it might have been prudent to have 5 to 10 minutes steady state just to make sure everything was lined out before even attempting to start the experiment. As an aside, the feedwater supply is not infinite, but limited to what the feedwater tank can hold. There's no information on the capacity of this tank, only that it weighs 204 tons when filled with water. Its diameter is approximately 30% larger than a steam drum, say 3,000 millimeters, and guessing 13 meters long for about 24,000 gallon capacity. The feedwater pumps can pump about 9,500 GPM, so the tank can be emptied under 3 minutes when no condensate returns. At 1:19 a.m. on the morning of the incident, about 1,000 GPM was needed to maintain the steady state drum level. If this tank was used for cooling rather than simple level control, there's a good chance this tank was emptied. As I alluded to earlier, Dyatlov had formed an impression the feedwater system was a cooling system. The reason for this was the feedwater tank was also piped to the bottom of the reactor. It's not necessarily a good idea to rob the system that ensures the MCPs won't cavitate for cooling capability where there are 3 backup systems able to provide that. Many have probably modeled the incident sending feedwater to the steam drums, but few have modeled the scenario where we're sending feedwater to both the steam drum and the bottom of the reactor. This was not only physically feasible, but probable, as it may have been the reason Dyatlov was so convinced the reactor could not explode. Here are a couple diagrams providing more detail about the feedwater system. On the left, we see the level controller as black dots and flow instrument details. Presumably, the flow meters are not capturing feedwater flows to the bottom of the reactor. On the right, we have a rare INSAG 7 diagram emphasizing the level controller valve this time with a strange reverse check valve symbol and unfortunately no flow meter details. We can clearly see that the feedwater flow is piped to an item 32 called an ECCS header. This ECCS header was a means to introduce adequate cooling downstream of the NCP pumps in case they may have failed. And we can see that a lot of the auxiliary cooling systems are nearby, and if the feedwater tank had gone empty, all these other auxiliary systems would be a means to try and get cooling to the bottom of the reactor. And this is what Akimov was presumably fiddling with these pumps 24, the diesel pumps, setting manual valves to route the flow back to the bottom of the reactor. He also likely fiddled with the ALS pumps 31 and the manual valves to push and route that water through the same line. All this manual intervention in the field would have been unnecessary had the ECCS system not been locked out to avoid unintentional triggering. So, the idea behind automation is to do all this in the control room rather than out in the field. Another diagram showing the feedwater piped to the bottom of the reactor was in the Vienna report, and we briefly looked at it earlier in the video when talking about the SEO and ECCS. Here is the diagram again, showing a single deaerator tank with two humps, a feed pump, automatic valves going to the RGK, distribution group collector. Here is a diagram reproduced by the IAEA showing the piping to the RGK and into the bottom of the reactor. The pipe is about 16 inches in diameter at the feedwater tank and about 12 inches after the split from left to right halves of the reactor core. Here is a 3D rendition showing the feedwater line going into each of the steam drums. It also may show the feedwater lines going into the bottom of the reactor, but it's hard to follow. Another 3D rendition with the RGK lines and where the feedwater is introduced downstream of the MCP pumps and individual check valves, not shown here. But we can see on this diagram the check valves that are so close to that line coming in, and introducing feed water this way with a fairly strong pump could interfere or potentially close the check valve on the MCP pump. Next, we have this trend that shows individual feed water flows from my favorite YouTube channel, That Chernobyl Guy. All his videos are great. There is a first attempt at 1:06 a.m. to inventory the steam drums, but fails. About 8,000 gallons are transferred from the feedwater tank and presumably just trickles down into the reactor. The second attempt at 1:19 a.m. appears to use the level controller based on the shape of the curves. We can verify that this trend matches the large strip chart. During the low flows at 1:12 a.m., the two flows total 50 kgs per second, which matches the large strip chart trend L. The trending program smoothed out a lot of the information seen at the top of these trends. However, this chart is not entirely accurate. The respective peaks that are off chart are reversed. In other words, the left side flow in blue is generally higher than the right side flow in red. There is an alternate version of the same chart where trend 2, the right half, is generally less than the left. This could indicate the feedwater tank is closer to the left side, and the pipe length to the right side flow meter is longer and has more resistance loss. It could also indicate an imbalance in the drum level between the left and the right sides, and it may have been a common occurrence. Trend S in the big strip chart presumably only records the average of the two. Notice the second inventory attempt is also shorter in magnitude than the first. This could indicate the control valve is in action trimming this flow, or there was less suction head. But the sharp peaks at the end potentially indicate flow to the bottom of the reactor was happening at the same time, and these automatic valves closed sequentially around 1:21 a.m. This caused a sudden surge of flow at the control valve, which reacted promptly to avoid overshooting the set point. But this created a weird peak at the end of the addition. There is yet another chart with the same data. This one starts at 1:21 a.m., presumably after the feed water valves to the bottom of the reactor are closed. It shows the peak and the decline for the rest of the time. Is the feed water tank empty by 1:23 a.m.? Is it struggling to push into the steam drum that is building pressure? This chart also shows feed water temperature at 155 degrees C at the start and building to 230 degrees C by the end. When the experiment is started, it is at 190 degrees C. This chart also shows the MCP volumetric flow in a long-term decrease since 1:21 a.m., whereas the large strip chart, trend K, shows a completely flat and constant trend during that time. Upon close inspection of this trend, it appears trend K only reflects one bank of MCP pumps. That is, it is only half the flow shown on this chart. Trend K may show the left bank only, the bank that may have behaved better than the right side. It seems the start of the experiment was an attempt to outrun the instability that was developing, such as the feedwater tank going empty, the feedwater temperature going to 190 degrees and above, losing a lot of MCP flow in the left bank, and potentially having a lower level in the left drum separator at the start. These problems taken together would increase the chance of cavitation in the grid-powered pumps on the left bank, for example. It may be that Dyatlov could not leave that night without running the experiment, no matter how high the stakes. Probably what did not happen was that he was unaware of the developing situation and everything was fine until the AZ5 button was pushed.